I want to first define the algorithm, the EM algorithm. I want to define the sequence of steps that you follow. It's basically two steps, an E step and an M step. Then I'll prove in the next slide that by following that rule, we're monotonically increasing the objective function. All right, so I've written the EM equality one more time. Remember, what we want to do is maximize this left-hand side over theta 1. We want to find the value of theta 1 that maximizes it. And we're going to work with the right-hand side in doing this. So we're going to work with this term, call this L, and it's going to be a function of x, which is our data, and a function of theta 1, because theta 2, again, is integrated out. So this term L is a function of the data and theta 1 only. And then here we have the Kullback-Leibler divergence. And even though these two values can change for different values of Q, for different distributions Q, the sum of the two values is always equal to the same thing. For particular, if we fix theta 1, then the sum of these two values equals the same thing for all distributions Q. So we're going to use that fact. Now the EM algorithm follows these two steps. Let's focus on one iteration t, and say that if we're in the tth iteration, what do we do to update theta 1 for the next iteration, t plus 1? So in that case, we're going to assume that we're given a value for theta 1 at iteration t. At the first iteration, this could perhaps be randomly initialized, but at the tth iteration, we have a value for theta 1. And our goal now is to find the value for theta 1 at iteration t plus 1. So this is our input, and this is going to be our output of the tth iteration. So we do two steps. The first step is the E step, and this actually has two sub-steps. The first part of the E step is to update the Q distribution. And so I put a subscript on Q to indicate what iteration it corresponds to, because this distribution is changing for each iteration. So the Q distribution that we define on theta 2 at iteration t is going to be equal to the conditional posterior of theta 2 given x and given the value of theta 1 at iteration t. Again, we're working only in an abstract setting here, so I can't tell you for this at this level that we're speaking what exactly these distributions are. But we assume that for the model we're working with, we can calculate this thing. So we set this Q distribution to be equal to the conditional posterior of theta 2 given the value of theta 1 at iteration t. Then the second part is to calculate this term using that exact Q distribution that we updated for the iteration. So we calculate L, and I'll put a subscript t here in order to indicate what the Q distribution is that we use, which is equal to this integral. So we take the expected log joint likelihood of x and theta 2 given theta 1, where we integrate out theta 2 using this Q distribution. And then we subtract this term here, which corresponds to splitting these two terms apart. Notice that that this term is a constant as far as theta 1 is concerned, so we're just going to ignore this part. This is the only part that is a function of theta 2. So now the E step is completed. We have this term, L sub t. It's a function of the data x and theta 1, and it was calculated using the Q distribution updated in iteration t. And then the second part is the M step, the maximization step. And in this step, we now treat this function as a function where we're free to change theta 1 to anything we want. And so we maximize it over theta 1. So that's the M step. And the output of that is the value of theta 1 for iteration t plus 1. So those are the two steps that we follow. It seems like a specific sequence of steps to follow. So how do we know that it's doing something good? In this slide, I have the proof of monotonic improvement. So I have the proof that by following those two steps in the previous slide, that the value of this objective function evaluated at theta 1 for the tth iteration is less than the value of the objective function using the value of theta 1 at the t plus first iteration. So what we're going to do is show that this term is less than or equal to this term. Remember, this is what we want to maximize over theta 1. And we have this sequence in between that's linking them. So this is another example where we're using analysis, just like in the boosting lecture, to prove that our algorithm is doing something good. The way that we do this is we use the EM equality. So we know that the log of the probability of x given theta 1 at iteration t is equal to the first term, the L function. So you can go back to the previous slide or perhaps write it down to plug in the values here, but I'm going to use this shorthand just to make it look more cleaner and more compact. So this log likelihood is equal to the L function evaluated at the same theta 1 at iteration t, plus the KL divergence between Q and the conditional posterior of theta 2 given x and given theta 1 at iteration t. And so notice I don't have a subscript t here, and I don't have a subscript t here, because this equality is true for all probability distributions that we can place on theta 2. Any probability distribution, this equality, the sum of these two terms is equal to this term. But the E step of the EM algorithm specifically sets Q to be equal to this conditional posterior. But the first step of the EM algorithm is to actually pick a value for Q. And so we let Q T of theta 2 be equal to P of theta 2 given x and given theta 1 at iteration t. So we actually set Q to be equal to this particular distribution. And so what does that do to this right-hand side? Well, it doesn't change the left-hand side, so it doesn't change the sum of the right-hand side, because we haven't changed theta 1, and the sum of the right-hand side is the same for all values of Q. However, by setting Q to be equal to this distribution at iteration t, we make this term equal to 0, because we've set the KL divergence between these two distributions to be equal to 0, which we know it occurs when we set this distribution equal to that distribution. Therefore, this term is equal to this term. So notice that I've now put a subscript t down here to indicate that I have calculated this thing using the distribution qt, so the q distribution at iteration t. And notice that I don't need to write this term anymore because I know that it equals 0 because these two distributions are the same. So this is the E step. These two lines constitute the E step of the EM algorithm. Now let's look at the M step. What do we do with the M step? We simply take this algorithm. We don't change the q distribution on t on theta 2, and so the subscript t here is not going to change because we use the same q distribution. However, we let this distribution now vary in theta 1. We don't enforce it to be evaluated at theta 1 for iteration t anymore. We let it be a free function, a function of theta 1, and now we maximize it over theta 1. So we know for a fact, even though we don't know what the specific value is that we get at for theta 1 at t plus 1, we know that whatever value it is, it has to be greater than the value at iteration t here, right? So we have not proved that this is greater than this, but we have shown already that this has got to be greater than this, because we literally maximize this thing over theta 1 and set that to be equal to theta 1 t plus 1. So if the value of theta 1 t doesn't maximize this thing, then this value is going to find the setting for theta 1 that does maximize it, and so it'll be greater then. if theta t plus 1 is equal to theta t, then it's equal. And so that's where the equality can come in. Okay, so this is the M step. So the E step took this right-hand side, put a particular QT in there to get rid of the KL divergence, but we still have an equality. The M step then let this variable theta 1 be free to change, and we changed it to the value that maximized this term here. So we now know that the update of this this first term of the KL of the right-hand side is greater than this term. However, we want to compare this term with this term. We don't want to compare this term with this term. So how can we now write this? How can we now achieve that goal? So notice that we can add a positive number to this term, and we aren't going to change the equality. So we can now add something positive to this thing to again have an inequality where we have now the sum of two things is greater than or equal to this value here. So the term that we add to this is going to be very cleverly chosen. We choose the KL divergence between QT. So remember, this is the Q distribution that we updated using the value of theta 1 at iteration t. But now it's the KL divergence between that Q distribution and the conditional posterior distribution of theta 2 given x and given theta 1, where we evaluate it at the value we get at t plus 1. So we plug in theta 1 at iteration t plus 1 here. So this term that we've now added is literally something that we arbitrarily chose to add. There's no reason why we have to add this term to the right-hand side. We're only doing it to help us prove what we want to prove. So we add this term. We know for a fact that this term has to be greater than 0 because we know that this distribution is not equal to this distribution, assuming that theta 1 changed between iteration t and t plus 1. We know that this thing is equal to this term here. And so if theta 1 has changed, then this distribution is not equal to this distribution. And so the KL divergence now is positive. So we've added a positive number to the right-hand side. And therefore, we don't have to worry about the inequality switching directions, because we've simply taken whatever number this is and added something positive to it. And so the sum of those two things has to be also greater than or equal to this term up here. Okay, finally, we want to simplify this thing. So first, let's now let Q suddenly be free to change. And now we simply remove the subscripts and we let Q be anything that we want it to be. However, we note that that these two things add up to the same thing for all values of Q. And then finally, we can recognize that the sum of these two terms is equal to the log of the likelihood of x, given the value of theta 1 at iteration t plus 1. So there's this sequence. If we follow it along, we find that this term is less than or equal to this term. And so the EM algorithm has defined a method for giving us a sequence of values for theta 1 that are monotonically increasing the log of the likelihood. It might help to look at a visual representation of this to help develop some more intuition about what's going on here. Here on the right-hand side, just for reference, I've shown the log of the likelihood of x given theta 1 that we want to maximize is equal to the L plus KL, where L is this term, KL is this term. So this is what we've already been working with. Now let's this value, this term has some particular value for a setting of theta 1. So imagine that we plug in a value for theta 1 here. It has some value which we're going to put here at this line. So imagine here that we've got the real line. We have 0 here. These are negative numbers, so these are less than 0 down here. We're going to put an arbitrary floor purely for visualization purposes, for no other reason. We'll put an arbitrary floor down here, much lower than all the other points, much more negative. And so the log of p of x given theta 1 for a particular theta 1 has a particular value. We don't know what it is, but it has a particular value. We also know that that's equal to L plus KL. And so L, because KL is greater than or equal to 0, this term L has to be less than this term. So we have this is less than L or equal to L, simply because this term has to be positive. So if we wanted to use the same visualization, we could put a line here for what L is equal to. And if it helps to view it from going up from some floor, you could also view it going up that way. So we have the log of p of x given theta 1 is here. That's equal to the equal to this term L plus the KL, which is a positive term. So this is the KL term. I sum this value plus the KL value, and I get the log of p of x given theta 1. Okay, so I now do EM. What does the E step of EM do? Well, the E step is going to take the Q distribution and set it to the conditional posterior. I'm going to make KL equal to 0. So the E step takes KL, sets it to 0, meaning that it finds a value for Q such that this term, L, is equal to this term, log px theta 1. So I've taken KL, by setting it to 0, I've increased this term such that this is equal to that. So that's what E has done, the E step has done. Now what has the M step done? It's taken this value, the old value of L, and found a new value for theta 1, such that this term increases. So by increasing that term, it's pushing the ceiling up, but at the same time, the KL divergence has also become non-negative, so we have even more slack here. And so we've taken our objective function and found a new value that's pushed it upwards like this.